my handle is there, post_silicon. Right, I've also posted a periodic table here because we will be referring from time to time, we'll be referring to the periodic table. And I've also went on again to post the exercise that we're busy with yesterday so that we can just go through it together. And then I've also included on this slide this table of physical constant, which is very important from time to time. We'll be referring to this table in today's lesson, to these tables in today's lesson, and also the lessons that will be following on Monday. So now the question was that we are busy with was a balloon is filled with 160 grams of argon gas. The pressure of the gas is 120 kilopascal at a temperature of 15 degrees Celsius. And then the question 5.1, that is the first question, you are asked to calculate the volume of the balloon. And 5.2, you have been asked, you have been told that the temperature of the gas is now increased by 20 degrees and the initial pressure is doubled. So that is the pressure will be moving from 120 to 240 kilopascal. And then also you have been told that temperature will be increasing by 20. It means it will be moving from 15 degrees Celsius to 35 degrees Celsius. So that's the changes in 5.2. But let's start with question 5.1. Calculate the volume of the balloon. So from this set of equations here, you can see, you can try to use this equation. P pressure is given, you are looking for the volume, and then you know that the R is the universal gas constant, which is this value here, 831 joule per Kelvin per mole. So it is a constant which is known, and temperature is given here is 15 degrees. It is given in terms of Celsius degrees. So we have to convert that to a Kelvin scale, which we can do. But now we do not have the N. So we are having two unknowns here. So what will be best? It is for us to look for a N. So N equals to, which is the number of moles, is a mass over molar mass. So we are given the mass of argon gas, which is 160 grams, and the molar mass of argon, let's go back to our periodic table. Argon is this gas here. It is 40, sorry about that. Argon is 40 grams per mole. So it's, the molar mass of argon is 40 grams per mole. So let's go there and then try to substitute in a relevant equation. So we're looking for N. So N will be mass is 160, and then the molar mass of argon is 40. So if you divide 160 by 40, it will give you 4 moles. Sorry, it should be moles, mole with no E. Right, let's carry on. Now we can be in a position to use this equation, PV equals to nRT. So we can say PV equals to nRT. We know that the pressure is 120 kilopascal. Kilo means 1,000, so it's 120,000 pascals. And then the volume is unknown, that's what we are looking for. And then number of moles, N is 4. And then R is 831. And then now the temperature T, temperature in Kelvin scale is 288. So where does the 288 come from? It is coming from 15 plus 273, which will give you 288. Remember, when we are giving your temperature in degrees Celsius, you have to convert that to Kelvin scale. So 15 degrees in Kelvin scale will be 288 Kelvin. So if you calculate, this will be 0.08 cubic meters. And remember, this is in cubic meters. Why is it in cubic meters? It's simply because in this particular equation, your volume is given in cubic meters. So that's your answer. Remember, always when you are using this equation, your volume will come out in cubic meters. Right, the next one we have been told that the temperature, calculate the new volume if the temperature of a gas is increased by 20 and then the initial pressure is doubled. So the temperature, let's try to solve this one. So in here, you are using the equation P1, this particular equation here. Let's just go back a bit. This equation here, P1 V1 over T1 equals to P2 V2 over T2. So that's the equation that we'll be using for this one. Now, what is the pressure? We are looking for the new volume. So pressure one, we know it is this 120 kilopascals. And then you are having also here your volume, your initial volume. And then now the pressure is being doubled. So the reason why they did not multiply by 1,000 is that you are multiplied by 1,000 on both sides. So you can say that 1,000 and 1,000 will be canceling out with each other because you are having multiplied by, because it's 120 kilopascal and the pressure is being doubled. So even if it was 120, the new pressure will now be 240. So because all of them are in kilopascals, so it means we are multiplying by 1,000 to represent a kilo. So in that case, because 1,000 is appearing on both sides, that is why it has been omitted in this calculation. It will, even if you include it, you'll get to the same answer. Now, temperature one, we have said that it is 288. It is coming from 15 plus 273, so it gives you 288. And then the other one, it is, if it is increasing by 20 for T2, temperature is increasing by 20, it means this will be 35. So 273 plus 35, it will be 308 Kelvin. So if you solve this one, you should be arriving, your answer should then be, sorry, just something here. Your answer should be coming back to be, let me just quickly, so it should be giving you 0.43 cubic meters. That should be your answer here. So now if you are also using this equation to say PV equals to nRT, look what is interesting here is that when we are using this equation, we are saying 240. So this is 240,000 kilopascal. So because there's no other kilopascal on the right of this pressure, so you substitute it fully to say 240,000 kilo, 240,000 pascals, and then multiply by the volume, and the N, the number of moles is still the same, the R is still the same, it's a universal constant, and the new temperature now is 308. Remember, it was 15, so they are saying it is increasing by 20, so it will be from 15, if we increase that by 20, it will be 35, 35. And then 35 plus 273, it will give you 308. So that will be the new temperature. And then this will give you the new volume. Right. So, and this can be converted to, if you want to convert this to decimeter cubic, you'll then see this will give you it should be 426,58 cubic decimeter, right? Now, today we are going to be looking at the quantitative aspect of chemical change. That is quantitative aspect of chemical change. And what do we mean by quantitative? Quantity means amount. We are interested in the amount, how the amount changes during this chemical change. Right, and this is also called stoichiometry. It's also called stoichiometric calculations. Now, at the end of the lesson, you should be able to understand what is meant by the mole concept. You should be able to explain and understand the mole concept. And you should be able to describe and define a mole. You should be also be in a position to describe the Avogadro's number, define molar mass, calculate the molar mass of a substance, and then also molar volumes of gases. You should be able to understand it, and also be in a position to state Avogadro's law. And you must also relate the STP to molar volume. What we mean by STP, we simply means standard temperature and pressure. So volume relationship in gaseous reactions, you should be able to understand that. And you should be able to interpret the equation in terms of volume relationship for gases. Right, furthermore, at the end of this lesson, you should be able to understand concentration of solutions, be in a position to define a concentration, what is meant by concentration, and be able to calculate concentration of a solution. And also there will be a bit more complex stoichiometric calculation, so you should be able to handle that. You should be able to determine the empirical formula and the molar formula of a compound, and you should be able to distinguish between the two. You should be able to determine the percentage yield of a chemical reaction, and be in a position to determine the percentage purity or percentage composition. That is, e.g., you should be able to know a percentage of calcium carbonate in an impure sample of seashell. Right, you should be also be in a position to do some stoichiometric calculation based on a balance equation, and this will include limiting reagent. And you can't be talking of limiting reagent without talking of excess reagent. So you should be knowing what is meant by limiting reagent and excess reagent. Right, let's look at the mole concept. What is a mole? A mole is the SI unit for amount of substance. That is, we define the amount of substance using the term mole. So we always use mole to define the amount of substance. So if we want to know the amount of substance, we use the mole. So what does 1 mole represent? So 1 mole of a substance is the amount of substance having the same number of particles as they are in 12 grams of carbon-12. Remember, when we are dealing with isotopes, we said that you are having carbon-12 and carbon-13, which are isotopes of carbon. So in here, when we are referring to a mole, we are saying 1 mole is the same as the amount of substance having the same number of particles as they are in 12 grams of carbon-12. Right. What is Avogadro's number? It is normally represented by this Na. It is the number of particles. These particles may be atoms, molecules, or formula units present in 1 mole. And then the Avogadro's number is the value of it is, we are looking for this 6,023 times 10 to the power 23 particles per mole. So every time when we are talking about a number of particles in a mole, we are talking about 6,023 times 10 to the power 23 particles. Right, and a molar mass of a substance is the mass of 1 mole of a substance. So if we are referring to a molar mass, it simply we are referring to the mass of 1 mole of a substance. So it is measured in grams per mole. So whenever we are given molar mass, let's say molar mass of carbon, or we have been talking about molar mass of argon gas, we are just referring to, it will be 40 grams per mole. Right, let's try to see if we can calculate the following. We'll do the first one, and then the other two you should be, I will just give you the, from the first one you should, and okay, let's do the first two together. Then from the second, from there going forward, you should be able to understand what we are doing. Let's go back to our periodic table. Remember, I've said that we are having sodium chloride. It is sodium and chloride. So let's go back to sodium chloride. To the periodic table. All right, now in the periodic table, okay, you are having sodium, which is having a molar mass. Look at the periodic table here. It is atomic, here it is what we call the relative atomic mass, which is normally the same as the molar mass. So molar mass of sodium will be 23, and then it is sodium chloride. Here's the chloride. So the molar mass of chlorine is 35,5. So sodium chloride will be 23 plus 35,5. So that this will now be the mass of sodium chloride. So let's see how we calculate the molar mass of sodium chloride. So this will then be sodium chloride. It will be 23 plus 35,5, which will give you 58,5 grams per mole. Now, the same thing applies to a calcium carbonate. You'll go to your periodic table, and your calcium, the molar mass of calcium will be 40, carbon will be 12, and then there are 3 oxygens. So it will be 3 times 16, which will be, this will be 48, plus 12, which will give you 60, plus 40, it will give you 100 grams per mole. The same can be done with calcium, so with potassium permanganate. It will give you, if you calculate it properly, it will give you 158 grams per mole. You are using the same procedure as the other two. So you will be expected to calculate the molar mass of different substances as we continue with this section. Right, let's look at molar volume of gases. We have said you must be able to understand the Avogadro's law. So Avogadro's law, it says 1 mole of any gas at the same will occupy the same volume at the same temperature and pressure. So 1 mole of any gas will have the same volume at the same temperature and pressure. So any gas, regardless of what the gas is, if it's 1 mole, it will occupy the same volume at the same temperature and pressure. Right, now 1 mole of any gas will occupy 22,4 cubic decimeter at 0 degrees or at 273 Kelvin, and at 1 atmospheric pressure, which is equivalent to 101,3 kilopascal. So what is standard STP? STP is standard temperature and pressure. So standard temperature, it is 0 degrees or 273 Kelvin, and standard pressure, it is 1 atmosphere, which is 101,3 kilopascal. So now we are saying that a molar gas volume, that is VM, VM will be used in equations and in calculation. At standard temperature and pressure will be 22,4 cubic decimeter per mole. That is the volume that will be occupied by a mole of any gas. Now, even if it's oxygen, it will also occupy this volume at STP. Even if it's hydrogen, even if it's methane, it will occupy the same volume. So it's just to emphasize this statement that I've made here on top. Now, you must be able to distinguish between scroll back a bit. You must be able to distinguish between standard temperature and room temperature. So standard temperature is at 0 degrees or 273 Kelvin. And then room temperature, it is 25 degrees, which is 298 Kelvin. Right. Concentration of, what is concentration of a solution? Concentration is the amount of solute per liter of a solution. So now let's try to define it further. We can say concentration is the amount of solute per unit volume. So now what do we mean by that? Is that normally we are using mole per cubic decimeter as the unit for concentration. So for purpose of this course, we will be class, we will be using unit of concentration as mole per cubic decimeter. But this mole per cubic decimeter is equivalent to the mole per liter. So some other texts might use mole per liter. So you must know that 1 liter is equals to 1 cubic decimeter. And then, so we are saying we define concentration as amount of solute per unit volume. So the unit volume here is cubic decimeter or liter, right? Now, concentration is calculated using the formula C equals to N over V, where N is the number of moles and V is the volume. So the volume that we'll be using here, it will be cubic decimeter. Right, let's try this. Try the following exercise to check your understanding. So I will be giving you say five or so minutes to be able to do that. Okay, let's just do it in 5 minutes, or let's say 6 minutes. So it's 11:25 by 11:31, you should be done. So you've got the next 5 minutes to do this activity, and then we'll do it together and check your solution.
Musala?
Hello?
Omolemo's asking that you just go back to the previous slide. He just wants you to take a picture.
Okay.
I think one more.
This one?
I think so. Umolemo, just respond in the chat for me if this is the one. Well, if he doesn't respond, we can go back.
All right.
Oh, he says he just needs the formula.
Oh. Okay, I think you can do up to 613. We'll talk about 614 later on. Just quickly do up to 613. Right, let's do it together again. You have been told that in an experiment, Elena has added 1,5 gram of sodium carbonate to hydrochloric acid, a volume of 306 cubic centimeter of carbon dioxide gas was formed and collected under standard pressure at room temperature. Take the molar gas volume at room temperature, that is Vm, to be 24,45 cubic decimeter. Right, the unbalanced equation for the reaction is given here. And then the first question is to define the term 1 mole of a substance. What is 1 mole of a substance? So 1 mole of a substance is the amount of substance having the same number of particles as they are there in 12 grams of carbon 12. Now, we are given this equation here and we are asked to balance it. Let's see how we go about balancing the equation. So this will be the equation. You'll be, okay, let's go back to the equation so that we can see the procedure. Right, you are having this equation, it is clearly unbalanced. Now let's try to balance it. If you look here, there are two atoms of sodium on the left. So we go to the right and we put a 2 here. What happens is that we are having how many of chlorine? If we put a 2 here, we'll be having 2 of chlorine. Then it means we have to put 2 here also. It has to be a 2 chlorine, and then on the left, and also how many hydrogen? 2 of them. On the left, if we put 2 here, and on the right, there are 2. And if we have placed 2 here and 2 here, it means there will be 2 chlorine atoms on the left and 2 chlorine atoms on the right. And then what about the carbons? Carbons, it will be 1 on the left and 1 on the right, sorry. And then what about the oxygen is 3 on the left, and then how many on the right is 2 plus 1, which gives us 3. So this is how the equation will look like. It will look like this. So this will be the balance equation. So balance, we just put 2 here and 2 here. Right, and the next question was calculate a mass of sodium carbonate that reacted. So let's just write what we were given here. You were given the amount of sodium carbonate was 1.5 gram of sodium carbonate, and also we are being told that the volume of the carbon dioxide, so volume of carbon dioxide that was released was 306 cubic centimeters. And then, okay, basically that's what the information that you needed. So let's carry on and see. Okay, we are also being told that molar volume is 24.45 cubic decimeter. So let's do it together to calculate the mass of sodium carbonate that would have reacted. So in doing that, we know that number of moles equals to what? Volume over molar volume. So here we are referring to oxygen here, sorry, to carbon dioxide that is being that is in a gaseous form. So number of moles will be the volume. Remember, give volume to be 2 cubic decimeters. So you divide by 1,000 to move from cubic centimeters to cubic decimeters. So it will give you 0.306, and then that will be the volume, and the molar volume, you have been told that it is 24.45. So the number of moles will be of carbon dioxide will be 0.125 mole of carbon dioxide. So, but remember, we are being asked to calculate the number of moles, the amount of, so let me just quickly go to the question. You have been asked to calculate the mass of sodium carbonate that have reacted. So in doing that, we have calculated now moles of carbon dioxide. So from the number of moles of carbon dioxide, we can say 1 mole of carbon dioxide is being produced whenever 1 mole of sodium carbonate react. So they are in a ratio of 1:1. So we can therefore say this, they are in a ratio of 1:1. So it means the number of sodium carbonate that would have reacted would be the same as number of carbon dioxide that would have been produced. So they are the same because they are in a ratio of 1:1. So after that, we can say the number of moles of sodium carbonate that would have reacted would be 0,125. Right. So from here, we can say number of moles equals to mass over molar mass. So in here, we would know this will be the number of moles, and that the mass is unknown. The molar mass is still it's known. We can calculate it because it will be sodium, which will be 23 times 2, which is 46. So sodium is 2 atoms of sodium. It will be 23 times 2, which is 46, plus carbon is 12, and then this one is oxygen. Oxygen is, if you look in your periodic table, it will be 3 times 16, which is 48. So 48 and 12 will give you 60, plus 46, it will give you 106. So if you divide by the molar mass of sodium carbonate, which is 106, you'll be getting the mass to be 1,33. So, and now because of rounding, your answer should be around this range. So I hope you have got something. So let's continue with something different in the next few minutes. So we're going to be talking about a bit more complex stoichiometric calculations. They are not that much complex, but they are not easy as the ones that you did in grade 10. So an empirical formula is the simplest whole number ratio of atoms in a compound. Empirical formula is the simplest whole number ratio of atoms in a compound. Whereas a molecular formula is the chemical formula that gives the total number of atoms of each element in a molecule of a substance. So, for instance, if you are having ethene molecule will be, let's say, ethene molecule will be C2H4. So that will be ethene molecule. So the molecular formula is that one of C2H4. But the empirical formula is the simplest whole number ratio of atoms. So it means it will be C1H2. So we'll deal with that when we deal with practical examples. So now let's look at percentage yield. Percentage yield is the actual yield over theoretical yield. And then the theoretical yield is the yield of a compound that has been calculated from a chemical reaction. It is the one that we calculate. And then the actual yield is the quantity that is physically or practically obtained. That is, if you calculate I'm having 2 grams of sodium reacting, for instance, with this number of this amount of the acid, they should be giving you this type of this amount of gas. So if you calculate that to get this amount of product, it is the theoretical yield. But when you weigh it or when you collect it and measure the volume or measure the number of moles or the mass, you are automatically going to get a different answer. So that one is called the actual yield. It is the physical quantity that you are getting, or the practical mass, the amount that you are obtaining. So, and then we have also talked about the limiting reagent. The limiting reagent is the reagent that is normally get used up. It limits the amount the reaction to continue. it's also limiting the amount, or it determines the amount of the product that can be formed. So the limiting reagent is the reagent that gets used up first in a reaction, and it it limits the reaction to continue. Once it gets one of the reactants, that is called the limiting reagent, gets used up, it means the reaction cannot continue. Right. Percentage composition is the mass of each atom present in the compound expressed as a percentage of the total mass of a compound. So for instance, if you are having, we have talked about the amount of calcium carbonate in, for argument's sake, in a sample of a seashell. So the percentage purity there, or percentage composition, will be given by the amount of pure substance over the amount of impure substance multiplied by 100. So percentage impurity will be the reverse, will be the amount of impure substance minus the amount of pure substance multiplied by the amount of impure substance, or the amount of the substance sample multiplied by 100. So this is basically one way of, you might be asked to determine the percentage impurity or percentage of contaminants. But we will be doing with those exercises. You should be able to follow this one. Now, let's look at this particular reaction in the remaining minutes. You have been told that zinc reacts with sulfuric acid according to the reaction below. And then the mass of zinc is recorded during the experiment is shown below. So the reaction stops after 2 minutes. So the first question here is that name the substance that is the limiting reagent. Right. So here you can see that the amount of zinc remains the same after 2 minutes. That is, zinc gets used up after 2 minutes. So it means zinc will be the limiting reagent. Now, the second question is calculate the initial concentration of sulfuric acid if 50 cubic centimeter of the acid was used. So you have to calculate the initial concentration of sulfuric acid if 50 cubic centimeter of acid was used. So let's try to calculate the concentration of the initial concentration of sulfuric acid.
Musala?
Hello?
We have to wrap up, eh?
All right. Okay. All right, because of time, remember I've said that we'll be coming back to 614. So tomorrow we'll start with 614, and then that we said you should skip in the previous exercise, and we'll deal with this one, calculate the initial amount of concentration of sulfuric acid if 50 cubic centimeter of acid was used. So we'll do that. And then remember the definitions that we have discussed here in this section. And then you must be able to do all calculation on ideal gases, and also on this stoichiometric calculation, you should be able to do that. And you can continue to use previous question paper from DBE. And then remember to practice. The more you practice, the better it will be. So tomorrow we'll continue with this activities on looking into quantitative aspect of chemical change. That will be continuation of today's lesson. will be looking into particularly the limiting reagent and percentage composition. All right, you can email me at masala.liburu@gmail.com or get me on social media. My handle there on Twitter is @masaladl and on Instagram is post_silicon. So see you tomorrow. Let's look at the limiting reagent and also percentage composition. So that's what we'll be doing tomorrow. So if you have time, please find time and go through that on your own so that when we do them together, you should be able to follow what we'll be doing. Thank you. Bye.